This is Studio One. Today let's talk about the deepest reaches of the universe. If you were given the chance to ask one ultimate question, what would it be? Are there aliens? Is there reincarnation? Or perhaps, what is the true meaning of life? For me, I would definitely ask how the universe came into being, how everything began. For scientists, understanding the origin of the universe is the ultimate question in the scientific community. Even when humanity knew little about Earth, we had already turned our gaze to the skies. To this day, humans have explored all the planets in the solar system, and our spacecraft have reached the heliopause, the outer edge of the sun's influence. But even if humanity could one day break through the solar system and the Milky Way, it would still be just a drop in the ocean compared to the vastness of the universe. That's why we launched the Hubble Space Telescope, which has captured images of the universe never seen before. And in 2021, the James Webb Space Telescope, hailed as the most powerful telescope in human history, was launched. According to the latest full-color images and spectral data transmitted back from the US, the Big Bang Theory seems to face serious challenges. This discovery has undoubtedly shocked scientists. As the most widely accepted model of the universe's origin, the Big Bang Theory has long been considered the most plausible explanation we can imagine. But do Webb's new findings suggest that our understanding of the universe might be fundamentally flawed? Today, let's dive into the James Webb Telescope and the question of the universe's origin, the Big Bang. Since humans began observing the universe, we have been pondering the question of its origin, proposing various hypotheses. For example, the infinite universe theory suggests that the universe emerged from nothingness, is infinitely large, and has no boundaries. Light could never travel from one end of the universe to the other. There's also the Big Bounce theory, which posits that the universe undergoes cycles of expansion and contraction. Our current universe is the result of a previous universe contracting and then expanding again. Then there's the multiverse theory, which suggests that our universe might be just one of countless parallel universes, each with different physical constants and fundamental laws. These famous theories of the universe's origin remain speculative and lack widespread convincing evidence. In 1922, astronomer Edwin Hubble observed that light from distant galaxies showed a red shift when passed through a spectroscope, meaning that the farther away a galaxy was, the redder its light appeared. He meticulously measured this phenomenon and created a graph showing that the farther a galaxy was from us, the redder it appeared. This red shift was systematic and universal, revealing a startling fact. If Earth is taken as a reference point, no matter which direction you look, all galaxies are moving away from us, and the farther away they are, the faster they are receding. In other words, the universe is expanding at an accelerating rate. Hubble derived a constant, now known as the Hubble constant, which represents the rate of the universe's expansion. He then theorized that if we reverse the galaxy's movement, they would have all been concentrated in a single point around 13.8 billion years ago, a point of infinite density and infinitesimal volume. Thus, Hubble's discovery suggested that our universe originated from the explosion of this singular point, giving birth to the Big Bang model. This simple yet profound hypothesis shocked the scientific world, especially because it contradicted the field equations of the greatest physicist of the time, Albert Einstein. In 1916, when Einstein published his theory of general relativity, he introduced a cosmological constant into his equations to maintain a stable, non-expanding universe. Upon hearing of Hubble's findings, Einstein visited the Mount Wilson Observatory, where Hubble worked, and observed the redshift phenomenon firsthand. Afterward, Einstein publicly admitted his mistake in letting subjective assumptions influence his scientific conclusions, and removed the cosmological constant from his equations. This led to the Einstein field equations as we know them today. Subsequently, numerous scientists validated this theoretical model through observations and calculations. However, the theory did not gain widespread acceptance until 1965, when Jewish scientists Arno Penzias and Robert Wilson accidentally discovered cosmic microwave background radiation, a faint glow of light permeating the universe. This discovery provided evidence of the afterglow and radiation from the Big Bang. They calculated that the universe cooled enough around 380,000 years after the Big Bang for matter to stabilize and photons to travel freely, allowing everything to take shape. The discovery of cosmic microwave background radiation solidified the Big Bang theory as the most widely accepted model of the universe's origin, as it explained many observational phenomena and aligned with multiple lines of evidence. However, Scientific theories are never absolute. They are based on current observations. As new data emerges, theories evolve. That's why humanity launched the James Webb Space Telescope, our most powerful observatory, to peer deeper into the cosmos than ever before. The James Webb Space Telescope. Astronomical telescopes generally fall into two categories: ground-based telescopes and space telescopes. Before rocket technology matured, ground-based telescopes were installed in high-altitude or desert regions, where the atmosphere is thinner, light pollution is minimal, and weather conditions are stable, all of which improve observation quality. However, they pale in comparison to space telescopes. Telescopes placed in Earth's orbit, far from the atmosphere, can reduce atmospheric interference and light pollution. They can also observe ultraviolet and X-ray wavelengths, as well as extremely distant and faint celestial objects, which ground-based telescopes cannot detect. The downside, however, is their exorbitant development and maintenance costs. By 2021, humanity had launched only 3 space telescopes. The Hubble Space Telescope, launched in 1990, primarily focused on observing the origin and evolution of the universe. The Chandra X-ray Observatory, launched in 1999, specialized in studying high-energy astrophysical phenomena such as black holes, neutron stars, and galaxy clusters. The Fermi Gamma Ray Space Telescope, launched in 2008, was designed to study gamma-ray bursts, pulsars, and other high-energy phenomena. The Hubble Space Telescope, in particular, has captured numerous deep space images, such as the famous Hubble Legacy Field. This is the most complete and comprehensive map of the universe to date, composed of 7,500 images taken over 16 years, containing approximately 265,000 galaxies. It has provided invaluable insights into the origins of the universe. Hubble was initially designed with a 15-year lifespan, meaning it was expected to retire by 2015. However, due to the lack of a replacement, Hubble has been kept operational through multiple repairs, despite its aging components and frequent malfunctions. Maintaining Hubble has cost over $10 billion, and continuing its operation is increasingly impractical. Hubble's maintenance heavily relied on space shuttles to transport astronauts for manual repairs. With the retirement of the U.S. space shuttle fleet in 2013, further maintenance became impossible. Consequently, Hubble is scheduled to retire in 2025 by lowering its orbit, re-entering Earth's atmosphere, and burning up over the Pacific Ocean. As early as 1996, NASA began seeking a replacement for Hubble, leading to the Next Generation Space Telescope project. The development of this telescope was long and arduous. Even Hubble's orbit, though high, was not entirely free from atmospheric interference, light pollution, and the threat of space debris. The James Webb Space Telescope, JWST, was designed to be launched to the second Lagrange point, L2, 1.5 million kilometers from Earth. This location is a gravitational equilibrium point where the combined gravitational forces of the Earth and Sun balance the orbital motion of a spacecraft. L2 offers a stable position and shields the telescope from the Sun's radiation, making it an ideal location for astronomical observations. However, this distance also means that JWST cannot be serviced or repaired once deployed. Its design and construction had to be flawless, with no room for error, or the entire $10 billion project would be wasted. The initial budget ballooned from $10 billion project would be wasted. The initial budget ballooned from $10 billion to $100 billion, and the launch date was repeatedly delayed from 2008 to 2021. In 2002, the telescope was renamed the James Webb Space Telescope in honor of NASA's second administrator, James Webb, who played a pivotal role in the Apollo moon landing program. The $10 billion JWST is a collaborative project between NASA, the European Space Agency, and the Canadian Space Agency. It is the most expensive and powerful telescope ever built. Compared to Hubble, JWST's primary mirror is 3 times larger in diameter, but only 1/3 the weight. The primary mirror consists of 18 hexagonal segments, measuring 6.5 meters across. The hexagonal design maximizes the use of space, provides better mechanical stability, and reduces overall weight, a concept inspired by the structural efficiency of honeycombs. The mirror segments are made of beryllium, one of the lightest metals, known for its excellent thermal stability, which prevents deformation at extremely low temperatures. However, beryllium is notoriously difficult to work with. The polishing precision required for each segment is within 10 nanometers, equivalent to manufacturing a 6.5-meter-wide computer chip. After polishing, the mirrors are coated with a 120-nanometer layer of gold to enhance their infrared reflectivity, giving the telescope its distinctive golden appearance. The primary mirror focuses light onto a smaller secondary mirror, which then directs it to a tertiary mirror, and finally, to the Integrated Science Instrument Module, ISIM, located behind the main mirror. Since the telescope is too large to fit into a rocket fully assembled, it was designed to fold and deploy in space. However, deploying the mirror segments 1.5 million kilometers from Earth was a high-stakes challenge. If the deployment failed, the entire $10 billion investment would be lost. JWST's primary mirror is exposed, while its most expensive scientific instruments are housed within the telescope's base, protected by a 5-layer sun shield. The sun shield, made of polyimide coated with a proprietary material, resembles a thin film, but is incredibly durable. It maintains the instruments at extremely low temperatures, shielding them from the sun's heat. The 5-layer design also provides some protection against small meteoroid impacts. As Hubble's successor, JWST's observational capabilities are 100 times greater. Its strategic position at L2 allows it to function as a time machine, peering billions of light-years into the past. JWST has 4 primary missions: locate the universe's first galaxies, study the evolution of galaxies, observe the formation of stars and planets within nebulae, investigate the potential for life in other planetary systems. These tasks include observing the most distant galaxies, the oldest stars, the largest black holes, supernova explosions, galaxy collisions, and pulsars. JWST will also study large-scale cosmic structures like galaxy clusters, gas clouds, and dust to unravel the mysteries of the universe's birth and evolution. Additionally, JWST can analyze the atmospheres of exoplanets tens to hundreds of light-years away. As a planet orbits its star, starlight passes through its atmosphere, leaving a spectral fingerprint. The presence of methane, oxygen, or other biomarkers could indicate conditions suitable for carbon-based life. Advanced civilizations might even leave detectable traces, such as atmospheric pollutants or metal particles. JWST can observe objects with a redshift of over 10, allowing it to study the universe's early history and the formation of the first celestial bodies after the Big Bang. One of its key missions is to observe the universe's earliest galaxies and stars, shedding light on how the cosmos began, a question that fascinates scientists the most. Recent images transmitted by JWST have already delivered astonishing results, challenging our understanding of the universe. The Cosmic Anomaly. The James Webb Space Telescope, JWST, was launched on December 25, 2021. On January 9th, its highly anticipated primary mirror and sun shield successfully deployed. After a 6-month journey, JWST arrived at the second Lagrange point, L2, in July 2022. Following several days of calibration, it captured its first image on July 12th. The telescope's primary mirror was aimed at a galaxy cluster 4.6 billion light-years away. The immense mass of these galaxies warps space-time, magnifying objects behind the cluster and allowing astronomers to peer even deeper into the cosmos. JWST's first image captured a tiny slice of the vast universe, with a resolution far surpassing Hubble's capabilities. The area covered in this image is equivalent to the size of a grain of sand, held at arm's length against the night sky. Yet, within this minuscule frame, thousands of galaxies are visible, including some of the oldest galaxies ever observed. By measuring the time elapsed since the Big Bang, analyzing the redshift of light from distant galaxies, and precisely calculating the cosmic microwave background radiation and the rate of cosmic expansion, scientists have estimated the universe's age to be approximately 13.797 billion years. This is the most accurate estimate of the universe's age based on current observations. According to these calculations, after the initial singularity exploded, the universe began expanding and cooling. Around 1 billion years later, roughly 12.8 billion years ago, hydrogen and helium coalesced to form the universe's first galaxies. This implies that the oldest galaxies in the universe are, at most, 12.8 billion years old. However, JWST's observations have challenged this timeline. Among the 4 most distant galaxies it has observed, one named Jades is estimated to be 13.4 billion years old, meaning it formed just 320 million years after the Big Bang. According to existing theories and calculations, the universe was still in a chaotic state at this time, making the formation of galaxies seemingly impossible. Furthermore, JWST has discovered several massive galaxies that existed 500 to 700 million years after the Big Bang. Their maturity and size suggest that the universe had already evolved for billions of years before the singularity exploded. These findings have cast doubt on the Big Bang theory, hinting that the universe might be much older than the currently estimated 13.8 billion years. In 2001, scientists observed a star named Methuselah, estimated to be around 13.9 billion years old, older than the universe itself. Dubbed the star that shouldn't exist, it underscores the limitations of current cosmological theories and the significant gaps in our understanding of the cosmos. In September 2019, German scientists recalculated the Hubble constant using gravitational lensing, arriving at a value of 82.4, significantly higher than the previous estimate of 73.4. This adjustment suggested that the universe might be only 11.4 billion years old. If true, the ancient galaxies observed by JWST would be far older than the universe itself. The Big Bang theory is not without its flaws. It struggles to explain issues such as cosmic inflation, the flatness problem, the monopole problem, and the unevenness of expansion. These challenges have led scientists to introduce new concepts like dark matter and dark energy. Thus, the Big Bang theory represents our current understanding of the universe's origin, but is by no means definitive. If JWST continues to discover galaxies older than the current estimated age of the universe, the Big Bang might merely be a small event within a much larger cosmic framework. It may not mark the beginning of time and space, but rather a localized phenomenon within an even greater universe. One possibility is that the universe is structured like concentric circles, with each universe nested within a larger one, extending infinitely. Alternatively, our universe might be one of many bubble universes within a vast multiverse. As our universe expands, it could collide with other bubble universes, allowing us to observe galaxies older than our own. These bubble universes might eventually merge into a greater cosmic ocean, though the scale of such a multiverse is beyond human comprehension. Humanity's understanding of the cosmos is like an expanding circle. As our knowledge grows, so does the boundary of the unknown. The more we learn, the more we realize how little we know. According to the second law of thermodynamics, disordered particles should not naturally form ordered structures like stars, planets, or intelligent beings capable of thought. At the limits of scientific inquiry, we are forced to turn to philosophy. Perhaps the purpose of the universe's evolution is to ensure that humans never fully unravel its ultimate mysteries. This perpetual quest for understanding fuels our curiosity, hope, and determination to explore the cosmos and find meaning in our existence. That's all for today's video. If you want to learn more about the mysteries of the universe and unsolved cosmic questions, remember to subscribe to Studio One. See you next time!